We have created an interactive model that brings a scene from a children's storybook to life using two interrelated working mechanisms. The chosen storybook is The Very Hungry Caterpillar, written and illustrated by Eric Carle. By investigating the storyline of The Very Hungry Caterpillar, we found that it is based on the life of a caterpillar that eats a range of different foods to prepare for hibernation and reappear as a butterfly. We have linked the researching component of our model to the investigating process outlined in the Australian curriculum. This process involves critiquing, exploring, and investigating needs and opportunities by critically reflecting on the intention, purpose, and operation of technologies and design solutions to best support the intended user. The scene we chose to recreate within our design was of the very hungry caterpillar eating the apple, as part of just one of the many different types of food the caterpillar consumes before it hibernates and transforms into a butterfly. Within this model, pneumatics is used for the apple to fall down the tree. During this time, the plunger of the syringe, located on the back of the model, comes out and hits the press switch, closing the electrical circuit, causing the caterpillar's eyes to alight. This represents the very hungry caterpillar's excitement and joy that the apple has fallen down the tree and become accessible to consume. Our model meets the size requirements outlined in the criteria. The length is 30 centimetres, the height is 21 centimetres, and the width is 11 centimetres. This is the model in action. This is how the systems interrelate.
Pneumatic systems use the energy stored in compressed air to do work. By controlling the release of the air pneumatic cylinders, we can turn that energy into movement. In relation to our model, as air is fed through the tubing, the syringe extends, causing the attached fishing wire to move with the attached weighted apple. Pneumatic systems were used instead of hydraulics because pneumatic systems easily channel airflow, can be loaded more safely, allows the area to remain clean and dry, applies a softer airflow movement, can be stored and is easily utilised. An electric circuit is like a pathway made of wires that electrons can flow through. A battery power source gives the force that makes the electrons move. When the electrons get to a device like a light bulb, they give it the power to make it work. A switch has been created using a cardboard flap and split pins to be used as conductive materials to close the circuit when these are touching, causing the light bulbs to alight. In our model, the systems interrelated by the force of the pneumatic system producing a vertical movement, giving the impression that an apple was falling from the tree. Once it reached the base of the model, the plunger from the bottom syringe extends fully, allowing it to make contact with the electrical switch, causing the electrical circuit to close. This makes the caterpillar's eyes light up.
The materials required for production included large and small styrofoam balls, 2 large syringes, plastic tubing, fishing wire, a sinker, a brass eyelet, a fishing swivel, 2 light bulbs, bulb holders, electrical wire, 1 AA battery, a battery holder, coloured paint, coloured markers, pipe cleaners, green paper, felt, and toothpicks. We also used a range of recyclable materials, including a shoebox, a singular egg carton, cardboard, a plastic container, bottle lid, and synthetic grass. This demonstrates to children the simple steps that lead to sustainable decisions to support the world we live in. Additional materials were used as joining techniques, including a wooden skewer, blue tack, hot glue, knots, thumbtacks, Velcro, a soldering iron, electrical tape, cable ties, and split pins.
Yep.
We have linked this section of our model to the produce process incorporated in the Australian curriculum. Producing design solutions should be suitable for a range of technologies contexts by selecting and manipulating a range of materials, systems, components, tools, and equipment creatively, competently and safely, and managing processes.
This model is robust and strong because we've used a solid foam shoebox for the foundation of the model. On the back of the model, we have used a clear box to firmly create a barrier over the electrical circuit to prevent contact and possible injury. We have also used cable ties that act as durable materials to make the syringe secure, enabling the systems to work efficiently.
A major challenge for us occurred when we were creating the pneumatic system. Our initial idea was to attach a piece of string to the end of a syringe. Using the loose end, we attached a styrofoam apple. However, this was too light to create movement, so a circular fishing sinker was used instead. We also substituted the string for fishing wire as this produced a more fluent movement.
Possible improvements that could have been made to the model include providing each light globe their own power source or power pack, to enhance the brightness of the globes. We could have also used a marble instead of a circular fishing sinker, as it is still weighted but would be lighter and hence more appropriate to use as a movable apple to ensure the fishing wire would not develop kinks and possibly break over time. Placement of the Hungry Caterpillar sign may have been more appropriate to attach on the side of the model rather than the front to ensure model components as the sun would be still fully visible. Additionally, using a larger syringe may have caused a more noticeable movement during the pneumatic process, whilst another effective and durable joining technique may have involved using double-sided tape that allows materials to be securely bonded and attached. From our model, we have created an Australian curriculum evaluation link that involves making judgments and assessing the quality and effectiveness of designed products that can be assessed by a criterion that supports recognised outcomes and success. Reflection on the designing and production processes allows suggestions of improvements to be made, supporting the ability to create future design solutions.
Safety is central to the design process as it allows children to use the teaching tool independently without teacher supervision as the risk of injury is eliminated. A plastic casing has been created to conceal the electrical components. The material used ensures that the system is still visible. This helps children understand and learn about how the system works. The inclusion of a latch allows for access if any faults need to be fixed.
Overall, we are very happy with our completed successful model that met the criteria standards and has the ability to be used as a future teaching tool within the classroom that activates children's sensory stimuli, is engaging, interactive, and is able to safely cater for the learning needs of all primary school students across the curriculum in many different learning areas.